Hey everyone, we're back. Thank you for the quiz and all the great photos. That worked out really easily. I hope people enjoyed the multicolored answers I gave you if you made a mistake on the quiz. If you got them all right, you didn't get to see the pretty colors, sorry. But we're gonna talk about the next chapter, 12.1, which is indefinite integrals. And before I tell you what that is, let's remember we're going to do some really high-level calculus here. F of x equals x squared. The derivative of that, of course, is 2x. And likewise, g of x is x squared plus 6. G prime of x, still going to be 2x, because the derivative of a constant is 0, because there's no slope to that. So here, I went from my function to the derivative. Going in this direction is differentiation. But if I go this way, if I go from the derivative to my function, if I go uphill instead of downhill, this is referred to as integration. Or it's sometimes called the antiderivative. Because basically we're doing the opposite thing that the derivative does. The derivative is the slope of the tangent lines. We're going to take the slopes of the tangent lines to figure out what the original function was. And integration looks like this. We'll have the integral, which is curvy line, of something like f prime of x. And we're always going to have a differential guy here next to it to tell us what variable are we operating on. You could have a function of x, y, and z, and we're only going to operate on x here. And in fact, this, when we take the derivative, when we take the integral of our derivative, we get our function back again, plus some kind of constant, which I'll talk about the constants. Those are very important. So going this way is the antiderivative, taking the derivative and undifferentiating it to get to the function. So this is what we're going to be talking about for the next two chapters. And there's a rule, let's see, powers of x formula. Okay, so we got a little kitty there. Who's that? Oh, that's Olive trying to see what's going on. So the powers of x formula says if I'm trying to take the integral of x to some exponent, x to the n, x to the third, x to the fourth, x to the fifth, whatever it is. If this is my derivative, like I have here, that I want to anti-differentiate, meaning I want to take the integral of it to find the original function, the way we do the math with this is we end up with x to the n plus 1 over n plus 1 plus my integration constant that we always have. And this is how we go in the integration direction from the derivative to the original function. So let's look over here at g of x here. Let's take the integral of 2x dx. Well, constants have no effect on the integral, and they can come out front. And so this is really what the function is that we're integrating. And the 2 is just there along for the ride, just like if you had a 2 here in front of the x squared, that 2 would be along for the ride, and it would get multiplied by this one when you take the derivative. So likewise, I can stick it out here, and it's not really going to contribute because it's still multiplying into it. So let's see, the rule says this is x to the first power. So the rule says x to the n plus 1 over n plus 1, and n is equal to 1 right here. So this would equal x to the n plus 1 over n plus 1. Oh, look at that. The 2's cancel and we get x squared plus c. Wow, this is our f of x again, or our g of x. Notice we don't know which one because we have this constant. It could be 0, and so this function could be f of x, or it could be 6, and this function could be g of x. We don't know which one. We would need more information, but what we've done is we've taken this function, which was our derivative, and we operated on it with the integration function, and it moved us back up here to the original function. Boop. Isn't that exciting? That is. This is the basic foundation for doing integrals of powers of x. And this is what we're going to do for a while here. And let's see, are there any questions? You in the back? Yeah, you? Question? Yeah, this is fun. Yes, that is true. This is fun. Okay, so we're going to go ahead. Oops. And let me stop this recording, and then we'll start another one showing how we apply it to the examples that are in the book and to the type of examples in the homework. Okay? Bye-bye. Stop.